Hello, everyone. Welcome to the Southwest Environmental Finance Center's podcast, or I'm sorry, training series, our webinar training series. My name's AJ, and this is the Tribal Wastewater Operator Certification webinar series. Today's topic will be advanced wastewater math. Just a reminder, we are the Southwest Environmental Finance Center, like I said at the top of the webinar. We are out of the School of Engineering at the University of New Mexico. My name is AJ Barney, and I'm a research engineer. I am also a state certified operator level 4 in the state of New Mexico for wastewater. I have a background in operations as well as engineering. And then we are also joined today by Matt. He will be moderating and answering questions and starting and stopping our poll questions, all the stuff that we really need to make this interactive. For those of you that are unfamiliar, we do provide technical assistance in a variety of fields. If you have any questions about these, you can go to our website, but we provide technical assistance in the fields of needs assessments, funding and financing. We do a lot of peer-to-peer learning sessions, and then also, which this training and webinar falls under the category of, we do training for building capacity for operations. And we are, like we said, this is part of a series. We are in week number 9 of this series. So we only have one more week. So just a reminder, if you want to join us for our final series, our final segment, that will be on August 20th. And you'll just follow the same link that we have been working on. Finally, there's just a couple of final webinar logistics. This training has been submitted for pre-approval for continuing education hours. We are going to send out our slides a day or two after the webinar. We will also be sending out certificates for the webinar series after the final webinar in the series on August 20th. We will send out an evaluation that we'd really appreciate you guys filling out. And then also, if you are part of a group to get credit, make sure let us know who all is with you, and we can make sure that everyone gets credit for it and everyone gets a certification. Now, on to the information about today. So today's agenda, like we said, is going to be our advanced wastewater math. So what this is going to do, it's going to build on our previous webinar segment on beginner and introductory wastewater math. So we are going to kind of refresh on a couple topics we're not going to really do a whole lot of refresher, but we're going to build on that with some clarifier math. Then we're going to start moving on to our biological processes, such as our fixed film media math. Then we are going to talk about BOD and the different type of calculations that we may perform for our BOD. Then we will talk about disinfection, and then some of our process control math. So before we get started, though, I would like everyone to, and then also at some point, probably at the top of the hour, 2 o'clock, we will do a little 5-minute break just to give everyone time to stretch and a little mental break from the math part. Everyone, if we can make sure we have a pencil and paper and a calculator ready, because throughout this, I will be asking some questions that kind of act as a refresher and kind of build on some of the basic concepts that we need to make sure that we can continue to excel at this math. So I might ask you guys to calculate real quick a portion of the problem, and so you can kind of work together to solve some of these examples. With that, let's get started on our first concept. So the first one is going to be clarifier math. And if you guys remember from our previous webinar, we talked about things like detention times and volumes and flows, which is kind of the beginning calculations that kind of work for clarifiers. And then some of the math concepts that we'll talk about now kind of build on that as well. And you'll need to remember, okay, how do I calculate flow? How do I calculate volume? And you'll need those to make sure that we can be able to calculate these kind of things as well for our certifications for wastewater. Now, clarifiers are important because, or calculations for our clarifiers are important because they're used to determine if treatment conditions are meeting design parameters. Primarily, this is to make sure that flow and design results, or that the flow that we have in design will result in correct sedimentation. So we're making sure that there's enough detention time, there's enough surface area and weir length to make sure that's treating all the flow that's going to be coming in. Our sedimentation tank calculations indicate if changes to flow and sludge management are needed. And then these calculations are also best if used in conjunctions with some of our observable conditions, like a sludge blanket, specifically the depth of that sludge blanket and the surface quality. So this can help us understand if we need to maybe make some adjustments. We're not going to talk about detention time today because we did that in our last webinar. But for example, if we know what our design detention time is for our clarifier, and we notice that sludge is starting to become septic and float to the top, we can go to the drawing board and kind of be like, okay, what are our dimensions? What's our flow? Or do we have the correct detention time, or is that what's resulting in this condition? So while these calculations help us, they're more as a lot of time as kind of concrete proof to be like, okay, what is the issue with this, and how do we adjust it based on these conditions? Yeah, so that's why a lot of times for our clarifiers, detention time is so useful. But some other stuff, for example, if we're getting too many solids washing out in our process, if we're observing that we're getting short circuiting, some of the other things that we can take a look at might be our surface loading rate and our weir loading rate. So the first one, the weir loading rate, this measures the amount of water leaving a settling tank per linear unit of length of weir per day. We use this to ensure that our weirs are not hydraulically overloaded, and we calculate this to ensure that we have sufficient sedimentation, and that our solids, excess solids, are not passing on to our next process, which is to be like a biological process, which is to be our biological process, and we ensure that we are not overloading the next stage in our process, and they're able to treat correctly because we remove all the settable organics. For a typical clarifier, the recommended weir loading rate is between 10,000 and 20,000 gallons per day per foot. And this is going to be linear foot of weir. So typically what that equation is going to look like is our weir loading rate or weir overflow rate is equal to the flow rate over the weir length. We represent our flow rate as Q and our weir length as L. And the way that we want to kind of remember this equation is that whenever we see in like a word problem, what is the weir loading rate or weir overflow rate, that weir should indicate or set off a little alarm in our heads that says, hey, I should check, or I should think about finding a formula for our weir overflow rate. So let's go over a quick little example how to do this. We're not going to take a whole lot of time to do these, but we will just make sure we get a walkthrough so you guys can kind of see how this is done. So for a weir loading rate, the problem or an example of this might look something like this. The flow for a circular clarifier is 1.2 mgd with a 26-foot diameter. What is the weir overflow rate in gallons per foot of weir length per day? So, like we said, whenever we have kind of a word problem, we look for that word weir. And if we see that on here, weir overflow rate, we know that we have a formula that may work for this. Now, in a lot of like the formula sheets, such as the NMED or the ABC formula sheets, they may call it the weir loading rate. But because we know, or because we're kind of learning about the way to approach this is to remember some of those keywords or understand what it's asking for. We just kind of understand that the weir overflow rate and the weir loading rate are the same thing. So based on that, we decide to use our formula for the weir loading rate. And then it asks for it in gallons per foot of weir length per day. Now, the first thing we know that we have is we have our flow. Now, that's the top of the equation. However, we do know that it also states that it is in gallons per day, or that it's asking for it in gallons per day, whereas the flow our problem is giving it is MGD. So that also tells us that we need to make sure that we have a correct conversion. So that's another thing that we're going to kind of practice as we move through these problems, is understanding if we see something like flow, is it in the correct units, or do I need to do a quick unit conversion? And that goes for kind of any of the units that we are able to calculate. We want to make sure those units add up, or that the units that we're trying to identify, that's usually given in the problem, is what we're actually calculating. So given that, we also need to find our length. Now, we are not given the length directly in this question. However, we are given the diameter. If you guys remember from our previous training, the way that you would find the circumference of a circle is by multiplying the diameter of that circle by pi. And for a circular clarifiers, we always want to remember that that weir length is going to be the whole perimeter. It's going to coincide with the whole perimeter of the clarifier, which is why we use the clarifier circumference to calculate it, because they're the same thing. The clarifier circumference is going to equal the clarifier perimeter. So based on that, we can take that 26-foot diameter, because that's what's going to represent the uppercase D. We can plug it into our equation and multiply it by pi, which will equal 81.68 feet, or 26 pi feet. For some of us that like to kind of keep that in the equation and just calculate it later, it could kind of simplify it. So that's why I kind of gave the option to think about both. For our purposes, though, we'll use the 81.68. Now, as I mentioned previously, we had 1.26 MGD was the flow. So we were given a flow. However, it was not in the correct units at the time. So if we multiply that by 1 million, because there's 1 million gallons in an mg, we will get 1,200,000 gallons per day as our flow. So we can plug that into the equation that we started with, the weir loading rate equation, and that is represented by Q. So 1,200,000 gallons per day divided by that L that we calculated, the 81.68 feet. So by doing that, we just plug that into our calculator, and we would get 14,691 gallons per day per foot, which is also equal to the units that the question asked for, gallons per foot of weir length per day. So if you'll notice, the gallons is still in there. That goes on the, would go on the top of our units, and then it's per foot per day, and that can go in either order, which we kind of show in the answer that we wrote down here. Now, typically an operator certification would probably round this to about like the nearest 3 digits or so. So it may look something like 14,700 gallons per day per foot. Now, if you take your certification as part of a regulatory agency that tends to want something a little more strict, they, are a little more precise, they may give both these answers and ask for which one's better. And in that case, you would use the 14,691. But hopefully most of our tests are just trying to make sure that you're demonstrating your knowledge and not necessarily trying to get people to be as precise as possible and, super strict. And we could go with the 14,700. But yes, that is something just to be aware of. Now, another way this may be done, so would be for an example like this, where we have a rectangular sedimentation tank with a length of 12 feet, a width of 18 feet, and a depth of 11 feet that has a flow of 190,000 gallons per day. And then we would be asked to calculate the overflow rate of this sedimentation tank. Now, since this is a rectangle, we may have a caveat like this, that the influent enters on one wide side of the tank and the effluent exits on the other. So A smaller clarifier like this, that's rectangular. We may see this with things like our package plants and things like that, where there's just going to be the one weir on the effluent side of the clarifier. And in that case, we're going to calculate that L differently for this weir loading rate. So based on this, the question says that the influent enters on one wide side and exits as effluent on the other. So for me, that would indicate that the influent and effluent are entering and exiting on the 18-foot sides of the clarifier. So that would indicate that the weir length for this, that the uppercase L, will equal 18 feet. Now, we're given the flow rate, and that's RA in gallons per day, which is what the units are that we used for our previous example. Oh, and this is just showing that the flow is going to enter on one 18-foot side and exit on the other. Now, since we, just from the problem, we're able to identify that the 18 feet is going to be our L, and my uppercase Q, or the flow rate, is going to be 190,000 gallons per day. We can just go ahead and plug that into our equation and calculate it out as 10,556 gallons per day per foot. Now, you may look at this and notice that there were some dimensions in there that we didn't necessarily use, such as the length of 12 feet and the depth of 11 feet. Now, these are going to be used to calculate other types of design parameters, but for this equation, we didn't need them. And that's something to be able to, that we want to practice as well when we're getting ready for our certifications, is being able to filter out when we do and do not need certain pieces of information. Okay, so that's our second example of a weir loading rate. Now we're going to move on to surface loading rate, so which is a very similar design parameter. This typically measures the amount of water passing over a unit of surface area per day. Like we said, it's another parameter that indicates clarifiers are not hydraulically overrated, and it does have a direct relationship to the settable solids removal efficiency of sedimentation tanks. Because if you have too high of a surface loading rate, you will not have your solids settling correctly, and there will be a lot of them will be flowing over, and you'll be getting some of that short circuiting. It is recommended that you have a surface loading rate of between 300 and 1,200 gallons per day per square foot. Now, if you'll notice, that unit's a little different than our previous problem where we had feet and we talked about linear feet. This is square feet because we're talking about our surface loading rate. The equation to calculate this is going to be our surface loading rate is equal to the flow rate divided by my surface area. Again, we represent that flow rate with a Q. We represent our surface area here with an A. It can be either A or SA, capital area, but either way, it's area, so I'm going to represent it as A here. And then again, we use our surface as an indicator of what we're going to be calculating. And again, when we see surface, we think surface area, and we want to remember those dimensions that area is typically measured in, which is going to be my square footage, my acres, square meters, and that kind of thing. So here's an example of how we might calculate one of these examples. So this question asks, what is the surface loading rate of a circular clarifier with a depth of 8 feet, a diameter of 9 feet, and an effluent flow of 42,000 gallons per day? So based on this, we have our equation like we talked about. We have our surface loading rate, which we go ahead and calculate based on, or which we're going to utilize based on those signifiers that our question asks us for our surface loading rate. So typically you can find one of these formulas in our certification that says surface loading rate. It asks for that flow, which is given already in the problem. So that's our Q, our 42,000. But then we need to figure out our surface area. We kind of mentioned this earlier, that we're going to practice doing some of these equations. So this clarifier mentions that it's a circular clarifier with a depth of 8 feet and a diameter of 9 feet. So here's our first poll question. We're going to go ahead and practice some of that previous math that we've done. And I would like you guys to figure out what is the surface area of the clarifier that we're going to use to calculate the rest of our equation since we already have the flow. So as you can see, most of us answered, or the answer that was picked the most was 63.59 feet squared. And that is the correct answer. So let me show you guys why. If you remember from our last training, the surface area of a circle is equal to pi r squared. So all the answers I see are in square feet or cubic feet, which is good because at least we were using the, we weren't trying to convert anything that we didn't exist. So everyone understood this wasn't quite in gallons. Now, if you would have chose 254.47 square feet, that would probably be using our diameter squared times pi. And if we calculated 508.94 cubic feet, that would be the volume of this clarifier. And it's understandable that, I threw that extra dimension in there, that 8 feet again, to calculate that. But really all we needed was the diameter of our clarifier to calculate this. So you can either calculate the surface area of this by multiplying 0.785 times the diameter squared, or in my case, the way I like to do it is the pi times r squared. So we plug that, and if you'll remember, the radius is equal to half the diameter. So that's why I plug in 4.5 feet here. We go and utilize that in our equation. We square the 4.5 feet. We multiply that by pi, and that equals 63.59 square feet, or 20.25 pi feet squared. So that gives us everything we need for our equation. We have our flow, which was already given in the practice problem, and we have our surface area that we just calculated as 63.59. And when we plug those into the equation, we get approximately 660 gallons per day per feet squared. So that's how we calculate the surface loading rate. So those are all our equations for our surface area rate that kind of build on, like we said, those areas and volumes. So now we're going to talk about some of our biological calculations. So for us, in this training, these are going to most likely, or not most likely, these are going to specify our calculations used to determine how well biological processes are moving nutrients properly, and that the biological loading is not exceeding their design standards. For this section, we're going to be specifically talking about biological processes like lagoon ponds, trickling filters, and our rotating biological contactors, or RBCs. Now, these calculations tend to aid with determining how much flow should be going through these processes, what recirculation rates you might need to have, as well as other adjustments, including troubleshooting when you may have a problem. And then one of our most important concepts which we're going to use through the rest of the training, is going to be BOD, our biochemical oxygen demand. And they're important for understanding the wastewater strength and how much organic loading, biological loading, our different biological and secondary processes are able to handle and efficiently treat. So we kind of mentioned this a second ago when talking about our biochemical oxygen demand, but it is a measurement of the organic strength of our wastewater, which means how much oxygen may be consumed by the microorganisms in the wastewater as they consume the other organics. Now, when we're talking about BOD for wastewater and for wastewater analysis, it refers to the specific measurement of the amount of dissolved oxygen consumed by those aerobic organisms in 1 liter of wastewater. When we are running this through analysis, this typically refers to a test expressed as BOD5 and is measured in milligrams per liter, and refers to samples that are incubated for 5 days at 20 degrees Celsius. The BOD is measured before and after to calculate it. Now, BOD is important for our biological process because it aids in evaluating whether the wastewater treatment plant and processes are performing as they should. You can apply BOD calculations to all the biological processes to understand how much BOD is coming in and how much BOD is being removed by the process. The BOD levels tend to indicate the efficiency of organic pollutant removal, and the BOD levels help to anticipate the impact the treated wastewater could have on the environment. And if the BOD is too high, that means that when it gets into the wastewater, it would start to consume too much oxygen in the environment, and which can cause problems with the other organisms living in the receiving waters. A lot of times this is used as a design parameter for plants to meet your MPDS permit requirements. Typically, it's referred to as part of our 30-45 rule, where you're supposed to have a 30-day average of BOD, 30-day average of 30 milligrams or less of BOD, or a 7-day average of 45 milligrams per liter or less. So let's talk about some of those calculations that you may use when talking about BOD. So the first one is the actual BOD analysis equations that we have. A lot of times this is super useful for our, this is how our lab analysts will utilize BOD. So just calculating those BOD 5 tests, this is typically how the BOD concentration is calculated. You may have a seeded test, which is used for quality assurance, or the BOD unseeded, which is kind of just a raw measurement of how much BOD is being consumed by the wastewater, and a raw measurement of what the organic strength of if your wastewater samples is. Like I said, so there's that seeded one that's utilized for our quality assurance. And if you'll notice, the main difference is that it has a seed correction compared to the unseeded equation, which does not have a seed correction. They both state that you multiply a factor of 300 milliliters because that's the typical analysis and the standard method requirement for how much the sample should be diluted to. So with that, let me show you guys how we might use this equation and what kind of data we might see. So this is what a typical BOD problem might look like on an exam. So it states the dissolved oxygen of a sample from a wastewater treatment plant, treated effluent, was measured shortly after collection, and after being incubated at 20 degrees Celsius for 5 days, the following data was produced. Calculate the BOD 5. So the first thing that we're going to take a look at this is that it does say calculate the BOD, and we're going to use our BOD unseeded equation because we're not given any seed information. If you'll notice on here, the equation has your the dissolved oxygen on your initial sample versus the DO of the final after the 5 days. And that is given to us in the data set as your initial DO, so how much DO is in the sample, versus what the DO was after the sample. And what we do is we simply can take that information. We can take the influent DO, the 9.1 milligrams per liter. We can subtract from it the 5.5 milligrams per liter of the DO after 5 days. We keep that 300 milliliters, like we said, as the second part of that fraction, or top half part of the fraction. And then on the bottom, where we have sample volume, this would be our 50 milliliters, which is also given in our data set. And this is important to make sure that it's taking into account the dilution of our dissolved oxygen, or the dilution of our sample. So if we calculate that in our calculator, we would get 21.6 milligrams per liter. Now, the first set of data is our blank data, which shows that the initial DO of our blank sample was 9.1 milligrams per liter. And after it was incubated at the same in the same environment, it had a DO of 8.9 milligrams per liter. So the blank should have, this is another means of quality control, and our blank should have less than 2 milligrams per liter, or 0.2 milligrams per liter of DO consumed. And this would just be kind of, cross-contamination or bacteria that kind of just was in the environment, in the air, that kind of made its way in, or organics that were kind of just part of the wastewater blank. If it exceeds the 0.2 milligrams per liter, that kind of shows that there's more cross-contamination. So that's how we calculate the BOD for a unseeded sample. Now, as I mentioned, there's also calculations for a seeded, or yes, for a seeded sample. And the way this kind of data and this kind of practice problem may look is something like this, where the problem would state BOD tests were performed on a sample of wastewater treatment plant influent and control laboratory control bottles. Calculate the BOD5 of the plant influent based on the following data. So very similar to our unseeded practice problem, our seeded practice problem, we kind of take the same kind of take the same kind of formula, but because we see in our data set that it says seeded blank, we're going to utilize our BOD seeded problem. And the way that we calculate, so we already know what the dissolved oxygen on the influent is, and the dissolved final oxygen on the final. We already know what our initial DO and our final DO is, as well as our sample volume and how to find that. But now we need to figure out how to take into account this SCF, which is our seed correction factor. Now our seed correction factor is equal to the initial DO of the seed blank, the final DO of the seed blank, and the seed blank volume as it's analyzed. And then that whole mathematical concept is multiplied by the seed volume that's actually used in the sample. So what's actually happening here in practicality is you take a sample of seeded water that you know has bacteria in it, that you know is going to remove organics. You place it under the same conditions. You incubate it for 5 days at 20 degrees Celsius, and you measure the DO before and after. Now, these samples are typically highly diluted, and you don't know if there's enough bacteria in your regular sample that you want to calculate how much DO is going to be consumed and what's the actual wastewater strength. So you seed it. So you add a little extra bacteria that's going to help consume those biologicals and going to give you a more accurate idea of what your DO is. So that's where that quality assurance comes in. So you put a small amount of that seed in the sample that you collect from, say, your influent or wherever in your process you're doing. And then you also run that BOD5 test as well. You would also keep running your blank tests on that. And then so afterwards, what you do is you would take the DO that the seed consumes, you would plug it into your seed correction factor. So that's where we have the 8 milligrams per liter and the 6.8 milligrams per liter. So, and then the amount of seed volume is found here. So that's just the total amount that you use to calculate the BOD of the seed. And then you have to find the volume that you use here for your seed volume of your sample. That's the amount that you would have added to your regular sample for your actual wastewater. So the way we plug that in is going to be our 8 milligrams per liter minus my 6 milligrams per liter of the final DO. We divide that whole thing by the 3 milliliters of our seed volume, and we multiply that by the 1 milliliter of the seed spike added to the regular wastewater sample. That would equal 0.4 milligrams per liter. Now, to do the rest of our equation, we use just the influent BOD that was measured at a regular BOD test. I'm sorry, the initial BOD that was used for a BOD5 test, the final DO. We use the correction factor. We add that in, or in this case, it can be subtracted out. So we subtract from the initial DO the 3.0 milligrams per liter of our final DO, our seed correction factor. We also multiply that by the 300 milliliters for the total analysis volume, and we divide that by the amount of sample volume that was originally diluted from. So we plug all those in, and for this sample, we would get 276 milligrams per liter. So with that, we are going to practice this all together. Oh, and then again, that 8 milligrams per liter are our blank. We kind of show that the initial DO is 8 milligrams per liter, and the final DO is 7.9 milligrams per liter, which is less than that 0.2 milligrams per liter. So this is a valid sample. That's all we kind of use that blank data for. So given that, let's go ahead and practice problem 3. Matt, if you want to pull up Our next poll question. I'll go ahead and read this out aloud. So the dissolved oxygen of a primary effluent sample was measured shortly after collection. And after being incubated at 20 degrees Celsius for 5 days, the following data was produced. Calculate the BOD5. So with this, we can kind of just, we know there's no seed data. So we know that we can use our BOD unseeded problem. And we have all our information here. So let's go ahead and plug it into our equation and see how many of us can get it correct. All right, it looks like about most of us have submitted. We'll go ahead and end the poll and share the results. It looks like most of us got the correct answer. So let's go ahead and finish walking through this problem. So as you can see, we had our influent DO, like we said, that goes in where DO lowercase, or I'm sorry, DO sub I goes. That 3.7 goes where the DO sub F. So we subtract that 3.7 from the 8. Then we multiply it by my 300 milliliters and my 10 milliliters. The milliliter on the top and the milliliter on the bottom cancel out. So we're just left with milligrams per liter. And the when we plug it into our calculator, it equals 129 milligrams per liter, which most of us got. Very good job, guys. So there's that showing that a majority got the 129 milligrams per liter. Now, this is also a good point to kind of talk about how useful, this is a useful example for how samples can be used to assess the efficiency of your processes, and to be measured not just at the beginning of the process and not just at the end, but throughout, especially if you understand what the design parameters are or what the typical BOD is. So for primary clarifiers, in this example, the effluent BOD coming out of a primary clarifier should usually be between about 50 and 150 milligrams per liter. Our answer of 129 milligrams per liter is a little on the higher side of that range, but it's within that range. So that tells us, we probably have a good amount, especially if we compare it and we see that, there's 400 milligrams per liter of BOD or something coming in, we can show that a large amount or like 2/3 of our BOD is already removed in our clarifier before we even get to our BOD process. So that would show us that by using these samples, we can kind of understand what if our process is running correctly and efficiently. So now when it comes to organic loading, we do also need to understand how a lot of these BOD units work. So this is kind of a little bit of a refresher of unit conversions, but it's important. This kind of shows you how during our BOD loading, how we can cancel out some units. So BOD is measured in milligrams per liter. And if you remember, 1 milligram per liter is equal to 1 part per million. And the way you can represent this is 1 over a million. And I'll kind of show you why we get to that. And the reason is, we have 1 kilogram of water is also equal to 1 liter of water. When you represent 1 milligram per liter, if you multiply it by the conversion factor from kilograms to milligrams, so 1 kilogram is equal to 1 million milligrams. So if you do a unit conversion, you can place that kilograms over 1 million milligrams in the second part of a unit conversion because it's equal to itself and you're already multiplying it by itself. The milligrams per liter will cancel out. And then because a liter is equal to a kilogram, like we just state above it with a kilogram of water is equal to a liter of water, those cancel out as well. And you're left with just the numbers here, 1 over a million. So that's why a milligram per liter is equal to 1 part per million or 1 million. The reason this is useful is during a lot of these biological processes and our other treatment calculations, we have our BOD loading, which is important to measure. This is the way that this formula is typically represented is going to be our flow in MGD multiplied by our concentration in milligrams per liter multiplied by a unit conversion of 8.3 pounds per gallon. If we plug that into a unit conversion, we would have just the numbers that represent our unit values. A million gallons per day is equal to literally the number 1 million gallons over a day. We take that milligrams per liter becomes 1 over a million. Then we still have our 8.34 pounds per gallon. So that million cancels out with that million, that gallons cancels out with the gallons, and we're left with just pounds per day, whatever as in terms of the units. And then whatever the values are for the flow and that concentration, we multiply by 8.34, and that would give us how many pounds per day are actually part of our loading. So we're going to want to remember that throughout this process, especially that equation, the BOD loading, flow times concentration times 8.34. And as long as that flow is in MGD, the units will cancel out to pounds per day. So why is this important? Because we have things like our organic loading rate. This measures the amount of organic material typically expressed in that BOD loading applied to a treatment system per unit of media. This may be, like I said, these are going to be our fixed film medias, or if you'll remember from the beginning of this section, this may be our fixed film processes, which are going to be trickling filters, RBCs, it can be ponds, and those are typically going to be in volume or surface area. So the units for our organic loading processes will typically be measured in units of media per day. Now, again, these are used as a design parameter to ensure that regulatory compliance is being met and that our processes have enough space and media to actually consume or process and treat all the wastewater and the organics that's going to be in that wastewater. It's also a good performance monitoring indicator if you're doing it before or after to make sure that it is going to be ready for those for that organic loading of your wastewater. This typically applies to things like trickling filters, RBCs, and lagoons, like we mentioned. And it will usually be expressed in pounds per day per 1,000 cubic feet of volume a day, or it can also be 1,000 square feet as well. So it seems like an odd unit. I'll show you guys kind of how to use that though. For a couple of examples of how to use those problems are going to be for RBCs. We'll have our organic loading rate, which is measured in the organic loading, pounds of BOD per day over the surface area, and that's going to be in thousands of square feet. Now, if it's trickling filters, this will be typically organic loading in pounds of BOD per day over the media volume in thousands of cubic feet per day. So, like I said, it sounds a little odd, but we'll show you guys kind of how to do that. So for this, we have this is what that kind of problem might look at first for an RBC. So, or a rotating biological contactor, if you guys remember. So an RBC has an influent of 150,000 gallons per day with a BOD concentration of 180 milligrams per liter. So the total media surface area is 60,000 square feet. And then we're asked to calculate the organic load in pounds per day per thousands of square feet of media surface. So first, we identify what we're going to be calculating. We're going to be calculating the organic load based on this problem. And then we know what units we're going to calculate it in, pounds per day per 1,000, per thousands of square feet. And then we also know that it's for an RBC. So that's going to tell us also that it's square feet. And we're going to know, we're going to think about what type of surface area we're going to be using for this equation. So since it's an RBC, like we said, we're going to have the RBC specific organic loading rate equation. Now we have our flow, but the information needed isn't quite provided in the way that it should. So we know our flow, but then also we have the need to calculate our organic loading. So we don't actually have any of the information that we need right off the top, except for our surface area of the RBC. So since that loading isn't provided, we have to calculate that. The first thing we need to do is figure out how many, what the flow actually is. Now the flow is given in gallons per day. If you guys remember, this is not quite how it's represented in the equation. So this is a good time to double check something as well. We're going to do another poll question. Matt, if you'll pull up the next poll question. So here we're going to all provide some input of what flow we should use for this equation in MGD. We'll do this one as a quick one. We'll just do about 30 seconds. Good, so we'll just share the results. So most of us got it correct. It is 0.15 MGD. And if you'll recall, that's because we divide by 100 and we divide the 150,000 gallons per day by the we divide that by 1 million gallons, which is equal to 0.15 MGD. So based on this, we should have all the information we need to calculate our BOD. So we'll launch another poll question, poll number 4, Matt. And this will be, we're all together going to calculate our BOD loading. This will be a good little practice to calculate that as well. So that poll should be available. And we can, the equation's up there, and we should have all of our variables that we need to calculate this now. Again, this will be a quick one. We'll do about a little less than a minute. All right, so it looks like most of us got this again. So as you can see, all we simply do is going to plug that 0.15 MGD into the equation above. So our BOD loading is equal to 180 milligrams per liter multiplied by a flow of 0.15 MGD times the conversion factor of 8.34 pounds per gallon. And just like most of us answered, we'd have 225.18 pounds per day. So this one is one where we just multiply across and we just make sure the units are correct. So now that we have that loading and we have the surface area already on here, one last thing we need to do is our surface area is given in 60,000 square feet, but we need it in thousands of square feet. So this is isn't gonna feel quite intuitive, but we do need to practice this. This is not given in the correct way, but in order to get the unit in thousands of feet, we simply divide it by 1,000 as long as it's already in square feet. So we just divide 60,000 square feet, and now it's in 61,000 square feet. I believe that's how you say it. It's kind of something that we kind of just have to memorize as we keep in parentheses to be able to calculate this correctly. So since we have that now, we can fill in the rest of our information for the organic loading rate. So we take that loading rate that we had in our last poll question, which the answer was 225.18. Most of us guessed, or most of us answered correctly. And then we divide it by 61,000 square feet. So we're really just going to take that 225.18 and divide it by 60 and then keep our units. And this will equal 3.7 pounds per day per 1,000 square feet. So that's why we have to pull that 1,000 out. And if we don't do that, we can end up with a kind of larger number. Now, the typical loading for an RBC is 2.5 to 4 pounds of BOD per day per 1,000 square feet. So this gets us within that range, and we also have our correct units. We had another example of this. For this, we're given our flow in MGD, but it's asking the same thing. A flow of 1.5 MGD is applied to a trickling filter. Now, because it's a trickling filter, that should let us know that we should be looking for volume. However, this trickling filter has a diameter of 48 feet and a depth of 5 feet. And it mentions that the incoming BOD concentration is 130 milligrams per liter. So then we need to calculate the organic loading rate on the filter in pounds per day per 1,000 cubic feet. So same thing, we're going to have to adjust that later to make sure that we account for the 1,000 feet. But right now, we don't have any of our information. So the first thing we want to do is, so like we said, we don't have our volume and we don't have our loading. However, we can calculate that with the same equation. So this doesn't change. We just take our flow, which is already in MGD, multiply it by our concentration, and then we can multiply it by the conversion factor. Now, to find the volume of the trickling filter, we're going to use one way to measure it is pi over 4 times my diameter squared times my height. That pi over 4 is that 0.785 some of us are familiar with. So let's go ahead and calculate those real quick. The loading rate is going to, when we plug those variables that we mentioned in, going to be equal to 1,626.3 pounds per day. Then we measure our volume, so that pi, then we calculate our volume, which is going to be our pi over 4 times my diameter squared times my height. We're given my diameter as 48 feet and a depth of 5 feet, so we can easily just plug those in. We measure my 0.785 times my 48 feet squared times my 5 feet. This equals 9,042.2 square feet or cubic feet. Now, when we plug that in, it's actually going to be 1,626.3 pounds of BOD per day over 9.432 thousands of cubic feet. And that's because we're actually, we divided that 9,043.2 by 1,000. So we pull those units out and then we plug this into our calculator. We should get about 180 pounds per day per 1,000 cubic foot. So with that, let's go and take a little 5-minute break. It's 2 o'clock. Okay, so we're going to get started again. Just a couple more of our fixed film media type of equations that you might see. We have some examples of these, but we'll send them out with the slides. But for now, I'm just going to kind of go over like the basics of them. So there's also hydraulic loading rate. So these type of equations are used to determine if the total flow going over your fixed film media, if it's going to be overwhelming or not. One thing to just keep in mind with these is just making sure you get the correct units. You maybe be in cubic meter or cubic. Or these are always going to be in. These are not always going to be in square feet. But when we're practicing these, you want to make sure that if it's the units match what type of process they're going over. Very similar to some of those other previous examples. Then we also have our hydraulic retention time, which makes sure that flow is in contact with our media long enough. So this is typically things like our rotating biological contactors and our activated sludge. And this is typically calculated by the volume divided by the flow in gallons per minute, multiplied by a conversion factor of 60 minutes per hour. And this will give you your hydraulic retention time in hours. This is very similar to our detention time, and just make sure that it remains in the process long enough to be treated correctly. And the next section that we have is our disinfection math. So this is going to mostly refer to our chlorine math. We don't have any examples or concepts where we talk about things like this UV, but this is another typical process that's used for disinfection. This training will kind of focus on the chlorine math. But overall, our disinfection calculations tend to let us know that that our chlorine disinfection or other type of disinfection processes are adequate to remove all the pathogens or to sterilize all the pathogens in a proper way, so that our receiving waters do not have too many pathogens that can affect human life and our environmental health. A lot of times we have to disinfect to make sure that we meet our regulatory requirements. And then a lot of the math that we use is going to be used to make sure that we're putting enough chlorine in the water, or like our UV is high enough and stuff like that. But again, we're focusing on that kind of chlorine side. So for our chlorine disinfection, now chlorine is used to remove the pathogens and kill our pathogens, those disease-causing microorganisms for the effluent before it's discharging from our receiving waters. Disinfection is accomplished with liquid, the sodium hypochlorite version of chlorine, solid chlorine, which is our calcium hypochlorite, and gas chlorine. Typical variables for some of our disinfection may be chlorine dosage, chlorine demand, chlorine residual, and these are all in concentrations. A simple calculation to remember is our chlorine dosage is equal to my chlorine demand plus my chlorine residual. When we're working with chlorine, we want to identify what type of chlorine we're utilizing. This can usually be identified by the strength, the solution strength. If we're not given a strength, this may just be my gas chlorine. So we want to kind of look for, and when we have gas chlorine, it's going to be 100% strength. But we use kind of those indicators of the solution strength, or in the practice problems, what type of chlorine is being used, to understand how we might need to adjust our problems and adjust the solution strength that we're using. So this is kind of very similar to some of the math from the last training where we talked about our solution strength. I'm sorry, when we used our different decimals and percentages math. So we're going to do this one all together here in a second. But when we're given a solution strength practice problem, it may look something like this, where our wastewater treatment plant uses a 4% solution to disinfect treated wastewater. What is the strength of the solution expressed as a decimal? Matt, if you'll go ahead and launch the poll question. Oh, you know what, Matt, we kind of skipped over some of these. I think it's the next one, poll question 6. Thank you. So if you remember the formula for this, it's going to be our solution strength as a decimal is equal to the solution strength divided by 100%. So let's go ahead and try to all calculate that very quickly. We'll give everyone about 45 seconds or so. So these are our poll results. Most of us got this correct. It is 0.04. And the reason for that is, if you remember the way we set it up, this is going to look something like this. This is going to be that we take that 4% solution strength, we divide it by my 100% solution strength. If you'll remember, the units, the percentage sign, cancel each other out. So when we divide 4 by 100, we get 0.04. So, we kind of tripped you up a little bit there. It can be a little bit tricky trying to remember where the percentage sign goes. But if we're asking for it in a decimal, we'll just remember that we remove the percentage sign. So that's why we end up with that 0.04. So now a useful chlorine calculation that we'll usually use. Our chlorine, we have 3 things that we can calculate. We can calculate our chlorine dosage if we add the demand and the residual together. We can calculate the residual by adding the dosage minus the demand. And then we can understand our demand by calculating by subtracting our residual from our dosage. Now, in real world application, the only one that we're most likely to use in the field to calculate would be our chlorine demand, because we can easily measure how much dosage we're adding to the effluent, as well as our residual afterwards. Whereas it's harder to calculate how much demand is being consumed by the wastewater at the time. And then also we typically use our feed rate to calculate that dosage. Or if it's in the liquid form of the solution, we can measure it with a meter. And then our chlorine residual is typically measured with our lab equipment or our field lab equipment, such as those little colorimeters. And then one thing else, so that's going to be why that is really our easily one to calculate. And just one quick note that if we'll remember that's good for our operator certification, is that the residual chlorine is composed of free chlorine as well as our combined chlorine. The free chlorine is the unreacted chlorine that has reacted with water to form hypochlorous and hypochloric acid. But then our chlorine, our combined chlorine tends to be the chlorine that has reacted with ammonia. And that hypochlorous acid will form chloramines with that ammonia. And then the measurement of the remaining chlorine after it is all utilized is going to be that whole residual chlorine, which combines both of those. Now, to calculate our chlorine dosage, this problem may look something like this, where we would be asked to determine the chlorine demand of a treated wastewater effluent if the chlorine dosage used for disinfection is 8 milligrams per liter and the measured chlorine residual is 1.3. So if you'll remember, that chlorine demand is equal to your chlorine dosage minus the chlorine residual. We can go ahead and plug those into the equation. The 8 milligrams per liter is my dosage. The 1.3 milligrams per liter is what's left over after it's reacted with the wastewater. And that would leave us with 6.7 milligrams per liter. So these problems are pretty straightforward. They're usually just addition or subtraction. And we just need to know which variables go where. So that's how we can calculate what our demand is. And that helps us project how much chlorine we may need to use in the future on different types of wastewater. Now, the other part of chlorine that's important to understand is going to be our chlorine feed rate. And this is very similar to our BOD and our BOD loading, how much water is going through it. This is typically applied to liquid and gas chlorine based on our dosage, and it's measured in pounds per day, just like BOD. And then this equation can also be moved around to understand how much dosage is being applied to our wastewater. And the equation for this, just like our BOD loading, our chlorine feed rate is going to be our flow times our dosage times that same conversion factor of 8.34 pounds per gallon. And if you remember, those gallons cancel out. The million cancels with the milligrams per liter because a milligram per liter is equal to a part per million. That leaves us with the pounds per day. So let's kind of go over a quick example of that. So this is what that kind of problem may look like to calculate the feed or what kind of feed we want to add to wastewater. So the wastewater treatment plant treats 2.8 millions of gallons a day of raw wastewater. The plant has a target dosage of 2.5 milligrams per liter. How many pounds per day of 65% strength HCH would you need to meet this goal? Now, when we have a different strength percentage that's not gas, we do have to figure out how to apply that. And the way we do that is we actually divide that whole feed equation by the solution strength. So for this example, we have our flow given in MGD, so those units are already correct. Our dosage is given as milligrams per liter of 2.5, so that's already correct. However, our solution strength is in a percentage and it needs to be in a decimal. So we plug that into our equation, we would have 2.8 MGD times 2.5 milligrams per liter times 8.34 pounds per gallon divided by 0.65. And this would be that 89.8 pounds per day. So we were able to get to our correct units because we were already in MGD and milligrams per liter. Now, like we said, we can rearrange these problems. Chlorine dosage can be calculated as the feed divided by the flow and that conversion factor, or if it's in HT, that first one would be for gas, and then if it's in HTH, or even if we're using liquid, we can use that decimal, or we can use the solution strength to adjust this as well. We would add the solution strength on top of that. So the dosage would be our feed multiplied by our solution strength divided by the product of the flow and the conversion factor. Like we said, that's used for the HCH or the liquid bleach. So the way we do that then, if we're including our solution strength. So for this example, we would have a chlorinator is set to feed 417 pounds per day of 12% chlorine bleach to treat a flow of 2 MGD. What will the resulting chlorine dosage be? So, like we said, so from the equation, it's asking what the dosage is in milligrams per liter. We have that equation from earlier. We say that we're using liquid bleach, so we use the equation that takes into account the solution strength. And those variables are all already here. We have the feed in pounds per day. We have the solution strength in as 12%. And then we also have the flow. Now we do, again, need to correct or make sure our solution strength is in the correct units. I asked for it in the decimal units. So we would divide my 12% by my 100%, and that would equal my 0.12. So again, I canceled out the percentage sign and I don't need it anymore. When we plug all those variables into our equation, we have the chlorine dosage is equal to the loading of 417 pounds per day times the solution strength of 0.12. This is divided by the product of our flow of 2 mgd and the conversion factor of 8.34 pounds per gallon. And this would equal 3 ppm or 3 milligrams per liter. Now, also with chlorination, a lot of times we want to be able to calculate our dechlorination as well. A typical chemical that's used to dechlorinate and remove chlorine from our wastewater is sulfur dioxide. Now, this is done because chlorine can cause things like fish kills and can deteriorate the environment if there's too much chlorine in the water. As we know, chlorine is very reactive, and while it's useful in removing pathogens, it's also useful, or it also kills other bacterial that is beneficial to wastewater. So that's why we want to dechlorinate. Sulfur dioxide is used is because it has similar molecular weight to chlorine, so it can be used almost to a 1-to-1 ratio. Typically, the way sulfur dioxide is applied to chlorine and wastewater is that you take the amount of residual that you typically have and you add a safety factor. A safety factor of 3 milligrams per liter is a typically used safety factor. So as you can see, we have a sulfur feed rate problem that is very similar to our chlorine feed and our BOD loading. And it kind of takes what that chlorine residual is, that typical average chlorine residual, plus the safety factor. Both of those are in concentration of milligrams per liter. This is multiplied by the flow, which is multiplied by my conversion factor. So the way this might look is you may have a question of something like this. A wastewater treatment plant with a 2.0 million gallons a day flow has an average chlorine residual of 4.5 milligrams per liter after disinfection treatment. What is the sulfur feed rate required to properly dechlorinate the wastewater if a safety factor of 3 milligrams per liter is desired? So these questions work a lot like our chlorine feed, but real quick, we identify first that we have a fluorine sulfur feed rate problem. So we go ahead and bring up our equation for our sulfur feed rate. And then we're already given our chlorine residual in a concentration. We're given our safety factor in a concentration. We're given our flow in mgd. So we can just go ahead and plug these right into the equation. So there's those concentrations and the flow. So if we put the 4.5 plus the 3 as our chlorine residual plus the safety factor of 3 milligrams per liter, I went ahead and factored out that milligrams per liter, so we can just add the variables of 4.5 and 3. We multiply that by my 2.0 millions of gallons per day, and we multiply that by my 8.34 pounds per gallon, and we get approximately 125 pounds per day. So that gives us how much sulfur, what the feed rate would need to be to offset the chlorine that is being added to disinfect our wastewater. And that wraps up our chlorine and disinfection calculations. So for the rest of the webinar, we'll go ahead and talk about our activated sludge and our process control calculations. This is going to be things like my F/M ratio, SVI, my sludge age, and my return sludge. Now, activated sludge calculations are important for a variety of reasons. They are used to optimize our activated sludge processes and determine possible corrections for underperforming processes. This is usually done to manipulate the microorganism population in terms of how much microbes are in the activated sludge and how old they are, because you kind of want to find a balance between the right amount, not too many, not too little, and you want a good sludge age that's not too old and not too young to make sure that you are processing the biologicals and utilizing oxygen most efficiently in those processes. These calculations are typically used to make recommendations for how much aeration is being applied to your activated sludge, how much you're wasting from your secondary clarifiers or directly from the waste, the activated sludge process, and then how much return activated sludge you're returning to your process. And then again, they help you troubleshoot to know, if you need to make any recommendations or adjustment to those parameters in the case that you have any foaming or bulking and other issues, and to address any regulatory issues as well. Now, the first calculation that we mentioned is our F to M ratio. This is our food to microbe ratio, and this represents the amount of organic material or food entering a bioreactor compared to the mass of microorganisms available to consume the organic material. So the BOD concentration, or the amount of BOD in the reactor, represents that food factor and the organic material that's available, whereas the MLVSS concentration represents the microorganisms in the reactor and the microorganisms that are available to consume that organic matter. Now, by monitoring the F to M ratio, we can ensure that our bioreactors are treating wastewater correctly and make sure that F to M, or our food to microbe ratio, is balanced, and that we can go ahead and meet our permit requirements with, that we have enough microbes to fully remove what's in the reactor and what's coming, the BOD that's coming through our plant. Now, a low F to M ratio tends to limit the microbial populations and decreases our wastewater treatment, while that high food to F to M ratio tends to lead to excessive sludge production. Our microbes will grow out of control and can also lead to treatment issues and create more unwanted solids. And then our F to M ratio, it's important to understand later, that tends to inversely correlate with the SRT or the MCRT, which is our sludge age. So if we have a high F to M ratio, we may have a low sludge age because we have too much food compared to the microbes that are in the sludge. Now, the way that we typically calculate this looks something like this. It's the total rate of applied food, which is a flow times our BOD, then the total microbes biomass, which is going to be the volume of our biological reactor, and the concentration of our MLVSS. Now, to expand on these, like we have kind of mentioned throughout, our Q represents our flow rate. Our BOD is going to be the concentration of our biochemical oxygen demand. And this specifically is going to be for the biological oxygen demand of the flow into the aeration tank. Our volume we will represent as our V, and this is the volume of that aeration reactor. And then we have two different examples of our suspended solids that are already in the aeration basin. So there's our mixed liquor suspended solids, or MLSS, which is the concentration of suspended solids in the aeration tank. And then we have our mixed liquor volatile suspended solids, which is the concentration of the living solids in the aeration tank. And we use the MLSS to calculate our MLVSS. These units tend to be measured in the mass of food divided by the microbial mass per day. And this could be pounds of BOD per day, or pounds of BOD per pounds of VSS per day, or kilograms of BOD per kilogram of VSS per day. And that VSS is just the volatile suspended solids. It's similar, it's taken from that MLVSS. Also, these units may be represented as just per day because you cancel out the pounds. Ideally, your F to M ratio in your wastewater reactors are going to be 0.2 to 0.6 pounds of BOD per pounds of VSS per day. But depending on the type of unit you have and your conditions, this could be a little higher or a little lower as well. Now, to actually apply this and calculate this, at first it seems a little complicated. It's like, where do we get the BOD? Where do we get the volume and the MLVSS? And why is this going to result in pounds per BOD over pounds of VSS per day? But the way we kind of will calculate that itself is we take the flow coming into the reactor, we measure the BOD concentration in that flow. Then we also, from our design specification, should have the volume of our reactor, and we can calculate our. Then we multiply that by the MLVSS concentration. Now, sometimes you add in your 8.34 pounds. You add your conversion factors on there, but they tend to be, and that would give you your pounds per BOD per pounds of ESS per day. If you applied that conversion factor, you can cancel out your millions of gallons, your concentration, your cancel with the milligrams per liter in both of the conversion factors. The day is left over. Now, because the conversion factor is the same as on top as on the bottom, you really don't even need it. And then also the only thing left is day. Which is a lot of times why you might just represent it as F-to-M ratio per day. To kind of simplify that, though, it's just going to be our BOD loading over our volatile suspended solids in the system. So I did a lot of talking about it, and it kind of maybe seems a little overcomplicated, but we're going to go over an example to kind of just show how this works in the field, or I'm sorry, in application. So this example would look something like this. A small wastewater plant has the following data. We have a BOD of 260 milligrams per liter. It has a biomass the biomass is equal to 75% of your solids. You have a tank volume of 84,000 gallons. You have a flow of 136,000 gallons per day. You have a concentration of 190 milligrams per liter. And then you'll be asked, what is the F-to-M ratio of this plant? So right off the top, the question is, what is the F-to-M ratio? We can underline that to identify what formula we're going to use, which is that F-to-M ratio is equal to pounds of BOD per pounds of VSS per day. And the first thing we need to do is calculate that MLVSS because we were not given it in our data. So to calculate the MLVSS, how do we do that? And the way we do that is we actually multiply the percentage of solids equal to the biomass multiplied by the MLSS. So that would equal 75% of my MLSS is equal to my MLVSS. So when I multiply my 75%, we take my 0.75, because that's how we usually multiply, or when we take the represent as a decimal and how we usually have to apply it to equal the correct number, times my 1900 milligrams per liter of MLSS, we get 1,425 milligrams per liter. And again, how do we get to that pounds of BOD per pounds of ESS per day with this data? Well, we have to plug in my BOD loading over my biomass, concentrated biomass solids. So we take my F-to-M ratio equation of my flow times my BOD, which we know is our loading, and then divide that by the amount of living suspended solids in my reactor. So we already have my flow. It's in gallons per day, 136,000 gallons per day. We have my BOD concentration of 260 milligrams per liter. We already have my tank volume of 84,000 gallons, and the concentration of living suspended solids will be that 14,000 or 1,425 milligrams per liter. So based on the data that we were able to calculate already, we have everything we need to calculate my F-to-M ratio. So we'll simply plug those into this equation. We'll get 136,000 gallons per day times 260 milligrams per liter divided by 84,000 gallons times 1,425 milligrams per liter. And this will give us 0.3 pounds of BOD per pounds of VSS per day. So with that, let's go ahead and practice this one more time. So this problem, another example of this type of problem may read something like this. The following data was collected for the performance of an activated sludge plant. What is the F to M ratio for this plant? So we're given the BOD as 250 milligrams per liter. The biomass is equal to 80% of my solids. My tank volume is equal to 0.9 million gallons. My flow is 3.2 million gallons per day. And my MLSS is 3,100 milligrams per liter. Just real quick, again, when we're doing a word problem, we figure out what we're trying to find first, which is my F to M ratio. We know that to find my F to M ratio, I need the living component of my solids. So that'll bring up my next poll question, Matt, which is what is the MLVSS for this problem? So what is the living portion of that total suspended concentration? So I'll give you guys about a minute to do this one real quick. We'll give it another about 10 seconds. Just a quick hint for anyone trying to figure out where to go. If you remember, it's 80% of our solids, and our MLSS represents our solids. So you take 80% of that to calculate the MLVSS. All right, looks like we got half of our participants who've entered that. And here are those results. So most of us answered 2,480 milligrams per liter, which is the correct answer. So good job. So I'll go ahead and stop sharing that. So if you remember, the way we calculate that is we take that percentage and multiply it by our MLS concentration. So the biomass is equal to 80% of our solids. The solids is at 3,100 milligrams per liter. So we multiply that 80% times my MLSS concentration, and 0.8 times 3,100 is going to be equal to 2,480 milligrams per liter. Based on this, we'll do our next poll question. We're going to take the BOD loading and divide it by the mass of living concentration in the tank itself. We should have all the units we need. And we'll go ahead and, if we're going to launch that, Matt, poll question 8, we'll try to get this through and see if we can calculate that. So if you guys remember, the top part is going to be my BOD loading, and the bottom part will be my mass of living, my biomass. And we typically calculate that by taking how much liquid is in my reactor and multiplying the concentration of living suspended solids by that volume. All right, so as you guys can see, the most common answer is 0.36 pounds of BOD per pounds of ESS per day at 41%, and that is the correct answer. The second most common answer is 0.29 pounds of BOD per pounds of ESS per day, which is what you would get if you did not, if you used the MLSS instead of the MLVSS in the equation, which, you know, at least I like that we're at least possibly using, or maybe we just kind of guessed between the two of 0.36 and 0.29 because we remembered that the F to M ratio is usually a little lower, between 0.2 and 0.6, which isn't a bad strategy because you at least are able to get rid of two answers right off the bat. So in saying that, let's just show you guys kind of how that math works. So if you remember, our F to M equation is equal to the BOD loading, the flow times the BOD concentration, over the biomass, which is going to be my concentration of living suspended solids multiplied by my total volume of my reactor, the aeration basin. So we have 3.2 mgd multiplied by 250 milligrams per liter. We divide that by the product of 0.9 million gallons at 2,480 milligrams per liter. We put this in our calculators, and we should get 0.36 pounds of BOD per pounds of VSS per day. So good job there, everybody. Now, the next parameter we're going to talk about for our activated sludge processes that we can calculate is our sludge volume index. So the sludge volume index, or the SVI, is a parameter used to describe the settling characteristics of sludge in the activated sludge process. What we typically do is we measure the volume occupied by activated sludge after settling in an aeration tank for 30 minutes. This is usually tested using a lab test setting where we have 1 to 2 liters of activated sludge, and the sample is placed in a wide mouth clear cylinder beaker with a clear visible volume indicator. So it's just a big, even, those kind of Coke can looking cylinders that have, 1 to 2 liters as the measurement. You allow that sample to sit for 30 minutes. You measure it, what the sludge content of is, how much is settled after 30 minutes. And that gives you, and you're able to use that in your sludge volume index calculation. Typically, you will measure it, the sludge volume at 5 and 30 minutes. The 5 will kind of give you an indicator if your sludge is settling way too fast as well. And in that case, you may have kind of old sludge that may need to be addressed as well. But the equation for this is going to be your sludge volume index in milliliters per gram is equal to the sludge volume at 30 minutes over how much sludge, a sample volume after 30 minutes, or it is the sludge volume, over your total sample volume multiplied by a conversion factor of 1,000 milligrams per gram over your mixed liquor suspended solids concentration in milligrams per liter. So let's show you guys how to calculate this with a word problem. So the example of this might look something like an operator collecting his normal sample for an activated sludge plant, places 1 liter of mixed liquor in a wide mouth beaker. The MLSS concentration for this sample is 2,600 milligrams per liter, and the sludge volume after 30 minutes was 390 milliliters. Calculate the SVI. So once again, it's a word problem. We need to figure out what it's asking for. The final thing that it asks for is that it tells us to calculate the SVI. So that tells us that we need our SVI formula. Now then we need to look through our problem and see if we have the correct data. So the first thing we have is that we recorded that the volume of sludge after 30 minutes was 390 milliliters. We also have that the sludge sample was 1 liter. And then we have our MLSS concentration as 2,600 milligrams per liter. So we can simply plug all these numbers into our equation. So the V30 will be 390 milliliters. The V sample will be 1 liter. We'll multiply this by 1,000 milligrams per gram and divide that whole thing by 2,600 milligrams per liter. The 1 liter as part of the sample volume cancels out with the liter in milligrams per liter on the denominator. The milligrams in the conversion factor will cancel out with the milligrams in the denominator, and that leaves us with milliliters per gram. So our answer, when we plug this into our calculator, will be 150 milliliters per gram. Let's go over another quick example. Now, we have a poll question for this, but we're not going to do it. Matt, you don't have to upload it. I'll just walk you through how to do this real quick, just to make sure we can get to all our topics before 3 today. So our second example, very similar to the last one, states an operator collects his normal samples for an activated sludge plant and places 2 liters of mixed liquor in a wide mouth beaker. The MLSS concentration for this sample is 2,900 milligrams per liter, and the sludge volume after 30 minutes was 487. Calculate the SVI. So again, let's identify that we're calculating the SVI. Pull up our formula to calculate the SVI. Our V30 is that 487 milliliters. The one difference is our sample volume was actually 2 liters because we placed 2 liters in a beaker. So that's one thing that we need to keep an eye out and make sure that we're getting the correct volume of our sample. So this time it's going to be 2 liters for that. And then again, we maybe used a probe to calculate the MLSS at 2,900 milligrams per liter. We can plug that again into our equation where we have 487 milliliters over 2 liters. multiplied by my 1,000 milligrams per gram conversion factor, and we divide the whole thing by 2,900 milligrams per liter, and we get 84 milliliters per gram, which should be in our desired range. So then the next thing to make sure our activated sludge process is running correctly would be calculating our sludge age. The sludge age indicates the average amount of time that microorganisms or solids have spent in the activated sludge process. This ensures that the correct types of microbes are present and that our wastewater treatment is optimized. This is typically measured by the mass of solids in the aeration tank divided by the solids entering the aeration tank. So the operator's certification tests and plants can typically use a couple different versions of this. You may see your SRT, which is solids retention time, or your minimum cell retention time, which will be signified by MCRT. Now, a lot of these tests may use them kind of interchangeably. However, the Sac State course may kind of typically just use SRT, and they can kind of give just slightly different versions of the equation. MCRT equations sometimes do not include the TSS in the secondary clarifier or only account for your living solids. But the typical equation may look something like this. Your SRT or your MCRT would be equal to the pounds of total suspended solids in your aeration tank, the pounds of total suspended solids in your clarifier, and you would divide that by how much you're wasting and how much solids are actually leaving the aeration tank as well. And you can also show this as kilograms as opposed to pounds if you're using the metric system. And then sometimes if you're doing an activated sludge process with only a BOD removal, your typical SRT range will be about 1 to 5 days. So here's a couple examples of how these problems may be adjusted. So very similar to some of our other loading stuff, we have, in order to find the volume of our suspended solids, we would multiply the concentration times the volume of our aeration basin. To find it for our secondary clarifier, we would multiply our solids by the volume of our secondary clarifier. Then to find out how much solids are leaving the clarifier or the aeration process, we would have the total suspended solids in flowing out through the effluent and how much is wasted as well. Those units all cancel out, and we're kind of just left with the per days at the bottom of the denominator. Again, you can use that 8.34 pounds per day conversion factor to get rid of the gallons and make sure we're just doing the loadings. And you're just left with your pounds per day. But again, since you're doing it on the top and the bottom, you don't really need that if you don't want to. Now, if you're not able to measure your total suspended solids for your secondary clarifier, you would typically just use your same MLSS for your aeration basin as you have for your secondary clarifiers, and assume that they are at least close, or that you can use the same values. If your solids are immediately pumped from your secondary clarifier, you wouldn't even use a number for that because they would not be accounted for your sludge age. And then finally, sometimes your effluent solids are considered negligible as well. And some equations only account for your solids in the aeration basin and the solids that are being wasted. So that's something to just keep in mind and kind of be familiar with on our different tests and how those may be applied. So what does this actually look like in an equation, though, in a word problem? So this is what an example of that might look like. We might be given the following data for an activated sludge process and be told to calculate the SRT. As you can see, we have a nice long list of data on here, and we have to understand where each of these data points might go in a formula. For our knowledge before we jump into it, we're not going to need any conversion factors. I did this example just so we can just plug it straight into our equations. But With all word problems, we first want to identify what we're going to be calculating. So it'll be our SRT. And we know that when we talked about for like the ABC, they tend to use those interchangeably. So we upload our equation for SRT or MCRT in days. Now, the first term we're looking for is our volume of our aeration basin. It's given at the top of our data set in millions of gallons. The MLSS is what we use for our aeration basin solid. So we're going to multiply that to find the concentration in our aeration basin. The secondary clarifier volume is given as the second line in our data set. And then it's signified in the data set that we have the suspended solids for the secondary clarifier. So that's what we plug in our TSS sub SC. The flow of the effluent is going to be considered to be the same flow as the influent, since we're not getting any information about recirc rates or anything like that. We have the TSS of our effluent that would typically be measured, as it's leaving, or maybe in a lab analysis. But that is also labeled on the data set. So that would be where our TSS sub effluent, EFF, is. Then we have a flow of our WAS, which is going to be the sludge flow rate multiplied by the solids measured in that sludge, your waste suspended solids. Yeah, your waste sludge suspended solids. So this is very simple. We can just plug all of these directly in, our 0.09, 3200, the activated sludge, the volume of our secondary clarifier, the TSS of the secondary clarifier. Then on the bottom, again, we have the effluent is going to be equal to my influent. We have the concentration of my effluent solids, and we have the flow of my wasting and the solids concentration of my wasting. When we calculate these all together, we would get 3.11 days. Now, these problems do take a lot of practice to identify the variables, and it's not going to be all that simple. But we'll send out the slides so you guys can kind of use to practicing some of these, and we could also send out some of our practice problems as well with the slides. So as part of that, we also have our sludge wasting. This is the process by which our excess biomass, or MLSS, is removed from the activated sludge process and returned to, and it's referred to as our waste activated sludge, or our waste activated sludge, or our WAS. And typically the most important thing about the SRT is it helps us understand if we need to increase or decrease our sludge wasting to manipulate the F to M ratio or to manipulate our sludge age. So a lot of times that's the more practical use of these type of calculations. We have a limited control of how much influent and effluent we have and their associated biomass, but we can adjust how much we are wasting. And we can adjust that based on how much solids we're pumping from the secondary clarifier. We tend to rearrange our SRT equation to calculate those WAS rates. And that may look something like this. Your WAS rate is equal to your MLSS concentration multiplied by your volume of your aerator and your secondary clarifier. You divide that by your SRT, then you subtract the TSS times the TSS of your effluent and your flow of your effluent. You subtract the product of that from the initial or the first part of the equation, and then you divide that whole thing by the solids concentration of your WAS. And in this example, like we said, sometimes you treat your MLSS and your as the same concentration, your secondary clarifier, if you're not directly measuring that. Now, for this type of example, it may look something like this. You're given all the same parameters, what's in your aeration basin, what's in the secondary clarifier, the same parameters that we had previously, except we're not giving. So yeah, this one doesn't give the TSS of what's actually in the secondary clarifiers. But a question like this might read something like this. The data was collected for a conventional activated sludge plant that has experienced decreased treatment efficiency, and the data is provided below. To decrease the sludge activate age of the microbial population in the plant manager, in the plant, the manager would like to decrease the SRT to 6 days to more closely resemble the design specifications. What should the target sludge wasting rate be to accomplish this? So if you remember our equation, we are given the SRT, so we can plug that in as our MCRT. And then we're able to plug the rest of these in as long as we convert to the right units. Now, because our sludge wasting, did I calculate this? Oh, so if we plug these in using the MG, we plug these all into our equation, we would get that this is 0.705 million gallons per day, or 70,500 gallons per day. So we're not going to go through too quickly on this just because we don't have enough time. But I did want to show you how these variables could just kind of be plugged in here. But it is important to understand that 70,500 is quite a bit larger than that original QWAS, that 29,000 gallons per day. So if we do get something like this, we actually want to make sure that we don't exceed 10% of a process change per day. Because if we triple that wasting rate, it would be too drastic, and we'd likely overdo it, and we want to kind of increase our wasting over a couple of days to make sure that we're not upsetting the plant. So that's our final calculation that we kind of use for our activated sludge. And that kind of wraps up our presentation. Do we have any questions?